Alright, let's take a look at number 7. A company manufactures cameras and MP3 players. It costs this much for a camera, so much to assemble an MP3 player. You got your labor. Reading. Okay. Why is this split apart? I don't know. Let me see if I can fix that real quick. The bottom line is, how many cameras and MP3 players should the company make in order to maximize its profit? That last question tells us what the variables need to be. How many cameras and MP3 players? Alright, so that means the variable should be the number of cameras and the number of MP3 players. Okay, so we identified the variables. Now, writing the system. Okay, so we need to write down the constraints. So I scanned through looking for limitations. A constraint is a limitation. So they're saying what it costs, blah blah blah, what it takes. Okay, here comes the limitation. It says the company can spend no more than $1,260 each week for the cost of assembly. Alright, that sentence represents a limitation. Alright, we've got a maximum of assembly money. So we have an assembly constraint. So I will label it assembly. Alright, since this is an assembly constraint, I will scan through the problem looking for where it tells me the cost of assembly for each item. It's going to say, well, so much assembly for cameras and so much assembly for MP3 players. So let's check it out. Alright, $24 to assemble a camera and $48 to assemble an MP3 player. Alright, remember, cameras X, MP3 players Y. So that's one of those equations that writes itself. Well, it's an inequality. Alright, 24x, alright, $24 per camera plus 48y, $48 per MP3 player. So the cost of assembly is going to be 24x plus 48y. Okay, and this can be no more than $1,260. So that means it has to be less than or equal to $1,260. So there's your assembly constraint. Alright, the key is to group together things that mean the same. In this case, look at this key word. Assemble, assemble, assembly. Each of these numbers are assembly, alright? Assembly of a camera, assembly of an MP3 player, total cost of assembly. Alright, so any other limitation? See, now they start talking about labor. Labor. Okay, here comes the other constraint. The company has 110 labor hours available. Alright, that is another limitation. It's another constraint. Limitation. So let me highlight that up for you. Okay, labor. The company has 110 labor hours available. Alright, that's the total labor hours. So let's see, let's break it down by cameras and MP3 players. 5 labor hours to make a camera, 2 labor hours to make an MP3 player. So guess what this equation is going to be? First of all, let me label it. This is a labor limitation, a labor constraint. All right, 5 labor hours per camera, so that's 5x. All right, plus 2 labor hours per MP3 player, so that's 2y. Has to be less than or equal to the total labor hours, which is 110. All right, so those are the two main limitations. I mean, the problem comes to an end right after that. So you had to mention that. There's another constraint that's very important, and you must not leave it out. And we shall call it the reality constraint. And it's just common sense that you can't have negative MP3 players, and you cannot have negative cameras. So you can have 0 or greater, but when you're talking about physical objects, you can't have negative objects. So in other words, the number of cameras has got to be greater than or equal to 0, and the number of MP3 players has to be greater than or equal to 0. Do not leave off these two reality constraints when they ask you to write the system. So technically that is 4 constraints, 4 inequalities. Okay, so we wrote the system. Now, an objective function for profit, or I mean they just plain tell us it's profit. So just like we scanned through looking for assembly and labor hours, now we're going to look for where it says profit, and we'll highlight that. Boom, look at that, profit, just like that. The profit is $42 per camera and $61 per MP3 player. Okay, that's it. 42x plus 61y. So profit equals 42x plus 61y. Alright, that's it. We wrote an objective function for profit. And that's all I asked you to do for problem number 7. Okay, let's move on to problem number 8. Solve the following system. Oh no! A triple system. Oh my goodness. Whew, it's been a while. Let's see if we can remember how we used to do this. Part of the key was we took it 2 equations at a time. Alright, so for example, we could look at the top 2 equations as a pair, and then we could look at the bottom 2 equations as a pair. Alright, I think I'll zoom in a little first though. Now, one of the main things we need to do is eliminate a variable. So either the x's, the y's, or the z's. But whatever variable we eliminate, we have to eliminate the same variable in both pairs. So, notice that the y's are opposites in these in this pair, and they're also opposites already in the lower pair. So it would be perfect to do the top 2 and the bottom 2. But for the record, I could have made a pair out of the top 1 and the bottom 1, for example, if I had wanted to. But I don't. Not this time. Alright, so let's play these. I like to rewrite it just so it's super clear what I'm doing. Alright, so the top 2 equations look like this. We have our negative 2x minus 7y plus 6z equals 20. And we have 3x plus 7y minus 4z equals negative 10. Now normally we would have to multiply one or both of these equations to get opposites. But since the y's are already opposites, we can just draw a line and combine like terms. So putting these together, these x's will just give us x. Alright, of course these cancel out. Alright, so they're gone. Putting the z's together, that'll give us plus 2z. And putting these together will give us 10. Okay, put a little box around this. We'll need this later. So x plus 2z equals 10. That's our first box equation. Okay, let's see if we can keep this color coded. Alright, I think I'll go to purple next. So we will do the next pair of equations in purple. And the next pair look like this. Okay, we have 3x plus 7y minus 4z equals negative 10. Alright, and then we have negative 2x minus 7y plus 2z is equal to 4. Again, normally we would have to multiply to get opposites, but since we already have opposites, let's go ahead and use them. So these will cancel out. Putting these together will give us x. Putting these together gives us minus 2z and negative 6. Okay, so let's put a box around this one. Okay, so at this point we have two new equations. Alright, focus on the equations in the boxes. Alright, both of these equations only have two variables, x's and z's. So what we're going to do is we're going to take these two equations and put them together into a system of their own. So I'll keep it color coordinated for one more step. So I'm going to take this blue equation, which is x plus 2z equals 10, and I will take the purple equation, which is x minus 2z equals negative 6. Alright, well this problem is almost too easy because everything is just lining up for us, man. Because here again, we would want opposites. So normally we would have to multiply something to create opposites, but again, the z's are already opposites, so we might as well use it. So I'm just going to put this line and combine like terms. So putting these x's together will give me 2x. Okay, the z's cancel out, and putting these together will make 4. Okay, now this I can continue on and go ahead and solve it. Alright, so what should I do? So I could go ahead and divide both sides by 2. Alright, and that is going to give me x equals 2. Alright, so that is one of my 3 solutions. So I'm 1/3 of the way there. Now, once we have a system that has only 2 variables, we know how to get both of those variables. So we found x equals 2. But all I have to do is plug this back into one of the 2 original equations and I can get x. So I think I'll pick the blue one just for fun. Okay, I'm just putting a line to sort of separate. So I found x, so now I'm going to try to find z. That's what I meant to say. So looking at that blue equation again, it was x plus 2z is equal to 10. But now that I have x, watch what I can do. I can take this and I can substitute it in for x right now. So this is going to become 2 plus 2z is equal to 10. I can solve this for z right now. Okay, I'm going to subtract 2 from both sides. That will give me 2z is equal to 8. And then I can divide everything by 2. and that's going to give me z is equal to 4. Alright, check it out. So now I have x and z. So all I need is y. Alright, to find y, I will go back to one of the 3 original equations. I'll just use the bottom one. Let's see, do I have space over here? I do. Alright, the bottom equation, negative 2x minus 7y plus 2z equals 4. Alright, I could have used any of these 3 equations. I just picked the bottom one. You know, it has the smallest number, so why not? Alright, and the idea will be to take the z and the x and plug them both in where they go. Alright, so we know that x is 2, so this will become negative 2 times 2. We don't know y, so this will just stay negative 7y. But we know z. Z is 4, so this will become plus 2 times 4 is equal to 4. So y is my only variable, so I should be able to solve it. So this will become negative 4 minus 7y plus 8 is equal to 4. Okay, these two are on the same side. Alright, so I might as well combine those like terms. So negative 4 and 8 together make positive 4. So then I'll have negative 7y plus 4 is equal to 4. Okay, subtracting 4 from both sides, that's going to give me negative 7y is equal to 0, which there's nothing wrong with that. And finally, if I divide everything by negative 7, alright, well 0 divided by anything is 0, so I will have y equals 0. So at this point you can see I have found all 3 variables. So if I wanted to, I could make a nice ordered pair, ordered triple, I'm sorry, in the form x, comma, y, comma, z. Alright, 2, 0, and 4. Okay, I believe that was the last problem on this particular sheet. Alright, so I'm going to stop this video here, and you can pick up and review some more on the next video.